Bismillahirrahmanirrahim. Our honorable speakers, professors, lecturers, students, and all participants in this webinar. Assalamualaikum and good evening, everyone. Before we begin, let's start with the recital of Umul Kitab Al-Fatihah. I am Farish, a second year Bachelor of Science Mathematics student at UiTM, will be the moderator for today's webinar. Before we start, I would like to review a few items for today's event. For your information, this event is broadcast through Google Meet and the YouTube channel School of Mathematical Science KPPIM UiTM. Don't forget to like, comment, subscribe and share. The audience will have the opportunity to ask text questions to the speakers by typing your questions into the chat panel and also in the YouTube comment section. You may send in your question anytime during the presentation. We will collect and address them during the Q&A session at the end of today's presentation. And one more thing, we will have a photo session at the end of the webinar. Please prepare yourself for that moment. The feedback and attendance form will be given at the end of the webinar. For students, please prepare a scan of your student ID card to upload to the form. Ladies and gentlemen, linear algebra is a fundamental branch of mathematics focused on vectors, matrices, and linear transformation. It is a language of many scientific fields, providing tools to the model and solve system of linear equation and understand geometric concept in higher dimension. From computer graphics to quantum mechanics and machine learning to economics, linear algebra's applications are vast and essential. It enables the simplification of complex problems and the derivation of meaningful insight from large dataset. By mastering linear algebra, we gain the ability to navigate and manipulate the multi-dimensional spaces that underpin much of modern science and technology. And we have invited an expert to talk about this. Let me introduce our speaker. Dr. Gia Septiana Wulandari received her Bachelor of Science degree in Mathematics from Institute Teknologi Bandung, ITB, Indonesia in 2009 and the Master of Science degree in Computational Science from Kanazawa University, Japan and the Master of Science degree from ITB Indonesia in 2011 through a double degree program. In 2021, she received a PhD degree in computer science from University of York, UK. She is currently a lecturer at the Faculty of Informatics, Telkom University. Her research interests includes graph transformation and recommender system. And without further delay, let's welcome Dr. Gia.
Yeah, thank you very much, Faris, for the introduction. Hello, everyone. My name is Gia, as Faris introduced earlier. I will give some lectures about linear transformation today. Please let me share my screen first. Okay, can you see my screen?
Yes.
Okay, thank you. So today's topic is mastering linear transformation from theory to application, as requested by your lecturers. So today we will learn about some basic about linear transformation, and we will see some applications that related to this theory. So I believe we already learned before about matrices and also how to compute basis or dimension before in the previous week of this course. So maybe I will skip some part about that, assuming that you already master that part. As introduced before, my name is Gia Wulandari. I studied in ITB and then in Kanazawa University, and the last one is in the University of York. Mostly my thesis from bachelor to PhD was about mathematics. The first one is about graph theory, and then for master it was about computational science. Sorry, I think okay. Yeah, for my master degree, my thesis was about computational science. It is related to a bit of chemistry, and then for my PhD, I back to graph, but it is more about graph transformation, how we can transform a graph into another graph for reaching some goals. Okay. And today I will talk about a linear transformation. I will talk first about the basic of it. So I will introduce what is linear transformation actually is, and then we have something called kernel and also range for linear transformation. And then I will also talk about one-to-one and also on-to transformation for this kind of linear transformation and inverse of a linear transformation. And finally, we will see some applications in real life that is about linear transformation. So the first one, introduction to linear transformation. Oh, sorry, please. Okay. Yeah, linear transformation is a function from one vector space to another that respects the underlying or linear structure of each vector space. So if you maybe already familiar with functions, in functions we have some domains and we also have some codomains. So basically in linear transformation, we have a function, but the domain and also the codomain are vectors. Okay, and there are some properties that are satisfied by the functions. The properties that I mentioned before is about these two properties. So suppose it's supposed to be W. V and W are vector spaces. Then we may have a function, say T, from V to W. It is called a linear transformation if for all vectors in V and a constant, if we have a transformation of the vector A plus B, it will be equal of the addition of, I think we're back again. So these two properties must hold for the function. So the first one, if we have a transformation of two added vectors, then it will be equal to the addition of each transformation. And if we have a transformation of a vector times a scalar, then it must be equal to the scalar times the result of the transformation itself. And if V is equal to W, then the transformation, we can call it as a linear operation. So let's say we have a function from R2 to R3. Sorry, it keeps go out. I'll try to share screen instead. Okay, so let's say we have a function T T from R2 to R3. So from two-dimensional space to three-dimensional space. So let's say we have xy to x minus y, minus x, and then y. And we want to know if T is a linear transformation. So if it is a linear transformation, then the two properties must hold. The first one is this, and the second one is this. So we want to check these two properties for arbitrary vectors in R2. So for this example, the first one, we want to show that the first property holds. So we can see that the addition, transformation of A plus B will be equal to transformation of the result of the addition, right? So it is, if A is A1, A2, and B, factor B is B1, B2, then T A plus B will be T of this addition. And addition of two-dimensional spaces is like usual, it will be like this. And by the definition we have before in the example, it will be A1 plus B1 minus A2 plus B2 for the first one, because it is x minus y, the first element minus the second one. And then we have minus the second one, minus the first one, and then the second one. And by having some operation, we will have this in the end. And again, by checking the definition of the transformation we had before, we can write it as the transformation of A1, A2, and the second part is the transformation of B1 and B2, where this is actually the vector A, and this one is actually the vector B. So the first property holds, where T of vector A plus vector B is equal to T vector A plus T vector B. And we need to check the second property, that is if the transformation of a constant times a vector is equal to the transformation of that vector times that constant. So back again to the definition of the transformation. A times vector A means we have this alpha A1, alpha A2, and then based on the definition of the of the transformation, we have the first minus the second element, and then the minus the first element, and then the second element. And we also can write it like this, and it is indeed an alpha of times transformation of A1, A2, where this is actually alpha T vector A. Right, so because the true properties holds for the transformation, then we can conclude that the transformation is indeed a linear transformation. Then we have a counter example. So let's say we have a function T from matrix of size 2 times 2, and we map it into a scalar R. The definition of the transformation itself is a transformation of a matrix A become the determinant of A itself. So we want to know if T is a linear transformation. Then again, we need to check for any arbitrary two vectors A and B in matrix 2 times 2, then these two properties must hold. Since A and B, the vectors, are in matrix 2 times 2, then we can just write the vector A like this and the vector B like this for arbitrary A11, A12, and so on until B22. So from the first property, we can check what is the transformation of the addition of the two matrices. Right? So we add the matrices first. So we have this, and then we find the determinant of this matrix. And for determinant 2 times 2 matrix, we can just use a standard formula. And after some operations, we can see that it is not equals to the determinant of A plus determinant of B. Instead, we have some other remainder here. So it means the transformation is not a linear transformation. Actually, if you want to show the second one as well, for this case, the transformation of a scalar times the vector, which means matrix A, it is also result in the scalar, the square of the scalar times the transformation of A, which is not equals to what we want to have, which is this. So it is not equal. That's why by showing this part as well, you can prove that the transformation T is not a linear transformation. So you can show that a transformation is not a linear transformation by showing that either the first property doesn't hold or the second property doesn't hold. Okay, for another example, let's say we have a function now from polynomial, second order polynomial to two-dimensional array. Here we have, we want to know if T is a linear transformation. And also we want to know what is T of 1 plus x squared. Okay, then again, we will check the two properties. For the first one, initially we need to determine define what is the two scalar we have, the two vectors we have, A and B. Because it is second order polynomial, we can just write it like this. And then for the first property, we need to check if TA plus B is equal to TA plus TP. Like before, we find the addition result of two polynomials first, and then we check the transformation result based on the definition of the transformation itself. And after that, here we can see that we can write it like this. And based on the definition, again, this is the first polynomial, the vector A, and this part is the second polynomial, which is vector B. So indeed, T, the transformation of result of addition between A and B is equal to addition of transformation of A and transformation of B. So the first property holds for any A and B vectors, and we want to show that the second property also holds. So here we can see if we multiply vector A with a scalar first, we will have this. We will have this. So we will have alpha A1 plus alpha A2x plus alpha A3x squared. And based on the definition of the transformation, this equals to what we have here. So it is alpha A1 and so on. And we can also write it like this. And this part is actually the transformation of vector A itself based on the definition again. So because the first and the second properties hold for this transformation, then we can conclude that this transformation is a linear transformation. And then if we want to know what is the result of this transformation, then we can just use the definition of the transformation. So A will be equal to 1, B will be equal to 1, and C will be equal to 1. So the transformation result is 1 minus 1, and the second element is 1 minus 1 as well. So we will have 0, 0, or factor 0 as the result. And then in linear transformation, we also have something called transformation matrix. So if we have a linear transformation T from V to W, it can be represented as this. So transformation of a vector U is a matrix A times the vector U itself for all vector U in V. Then A, what we have here, is called the transformation matrix of T. Okay. For example, suppose a linear transformation we have from R2 to R3 is defined by this. We can also write it like this, right? Txy is equal to x minus y minus x and y. And it can also be written, the right-hand part, as this. It is x minus y, and then minus x, and then y. Then, as what it is defined before, T of a vector is a matrix transformation times the vector itself. So this matrix is the matrix transformation of this transformation. And there is a lemma that says if we have a transformation from nth dimensional space to mth dimensional space, then it is a linear transformation, then the size of the transformation matrix will be in m times n. Like for example, here we have 2 second dimensional space, 2 third dimensional space, so we have 3 times 2 matrix as the transformation matrix. Okay, we go to the next part, is about kernel and range. Suppose we have a transformation again, which is a linear transformation from V to W. Then every element of V that is mapped to 0 vector in W is called kernel of T. Okay, so we have V, and then we have W, and everything that is mapped to 0 vector in W is called kernel. Notation for kernel of T is ker_T, like this. And kernel of T can also be written like this. So it is every vector in V, which result in 0 vector after the transformation. And the set of all vectors in W that are images under T of at least 1 vector in V is called range of T. And the notation is RT. In short, kernel of T is null space of the matrix transformation of T, and the range of T is column space of the matrix transformation of T. For example, let's say we have a linear transformation from P2 to R2, and it is defined like this from a second order polynomial to a two-dimensional space. And then here we observe, then in the previous example, we know that the transformation 1 plus x plus x2 by this transformation is equal to 0 factor. It means that the polynomial we have here is a element or is a member of kernel T. But if we check this polynomial, then the transformation of it will be 1 minus 2 and then 1 minus 1. We have 1 minus 2, 1 minus 1, which is not a 0 factor. It means this polynomial is not in kernel of T. And then let's say we have a linear transformation from three-dimensional space to second order polynomial like this. So we have three elements here, A, B, C, and the transformation result in second order polynomial. Here we want to determine the basis and dimension of kernel T and also range T. Observe that for kernel, we want the result of transformation equals to 0 factor. 0 factor of polynomial is actually equals to 0, right? So we want to find ABC such that the result is 0. It means this part must be 0, this part must be 0, and the third part must be 0 as well. Or we can write it like this. So A plus B must be 0, 2A minus C must be 0, and 2A plus B plus C must be 0 as well. Or we can write it like this. All right, because we want this to be 0, this matrix can also be written like this. So the transformation of matrix T, so the transformation matrix for T is this. Because T of a factor is the matrix transformation times the factor. By doing, OBE means elementary linear operation. Elementary basic operation. So here we have the matrix and we want the result be 0, 0, 0. And by doing the operation, we will have this. It only happens when A is equal to 0, B equals to 0, and C equals to 0, which means kernel T is only 0 factors, or the basis of kernel T is empty set, or the dimension of kernel T is 0. And then for the range, we can see that the result of our basic operation is this, which means the column space basis of the matrix transformation is this. We got it from the column space. And then As a result, the range basis of T is this for the first one. We got it from here. And then this is the second one. We got it from here. And this is for the last one. We got it from the third basis. Hence, the dimension of range T is 3. For another example, let's say here we have transformation from 4-dimensional space to 3-dimensional space. So here we have 4-dimensional space goes into 3-dimensional space. And we want to determine again basis and also dimension of kernel T and also range of T. And again, for kernel, it means that we want this transformation equals to 0 factor, which means this transformation can also be written as this. And we can again find basic elementary operation for this matrix, like this. And the result of the operation will be like this one. Here we can see that we have a row of zeros here. So of course the kernel dimension is not 0 like the previous one. Here if we check the basis, we will have this 2, right? I assume that you already know how to get to this part from this part. Hence, the basis of kernel T is this from what we have here. And then the dimension of the basis of kernel T is 2, or we can also call it as nullity. Goes into the next topic is about one-to-one and also onto transformation. So like a function, if you remember, we also have one-to-one function and we also have onto function. It is similar to that because the linear transformation is also a function. Basically, if T is a linear transformation, T is said to be one-to-one if T maps distinct vectors in V into distinct vectors of in W. And T is said to be onto, or we can call it as onto W, if every vector in W is the image of at least one vector in V. It is similar to a function in general. So if every vector have distinct mapping, so distinct result to the codomain, then it is one-to-one, like this. So everyone has its own pair. But something like this, it is not one-to-one because this these two has the same result of the transformation. And these two also have the same result. So this one is not one-to-one. And then for onto means that every element we have in W is a result of transformation of at least one vector in V. So if we have V is mapped to W, then every element of W is in the range of T. Or we can say that the codomain of the function is W itself. The range. The range is the W itself. And then for this part, it is not onto, because we can see here the range is only part of the W. So not everything is a result of the transformation. Okay, so one-to-one means every vector has its own pair. So we don't share results in W to V. And then for onto means the range is the W itself. So suppose we have a transformation from R2 to R2. So it's a linear operator. Here we have the definition of the transformation. And we want to check if this transformation is an onto transformation or not. So again, onto transformation means that for every member of the codomain, it must be a result of transformation from any member of the domain, at least one. Okay, so suppose we have an arbitrary member of codomain. So because it is in R2, let's say we have AB as the member of R2. So AB is the result. And here we want to check, because it is arbitrary, we want to check if there exists XY in the domain such that the transformation of XY is equal to AB. Okay, because we want to check if here the codomain, every member of codomain is a result of transformation from some domain. Then we take arbitrary member from codomain, and we want to check if it is a result of some domain, member of domain. If yes, if we can always have XY such that the result of the transformation is AB, then it follows that the transformation is an onto transformation. So for the checking, again, suppose we have arbitrary AB in R2. And because we want to check if there is axis XY, it means the transformation itself is defined like this, and it must be equal to AB, right? And by elementary basic operation, here we can get that X will be equal to 2A minus B, and Y will be equal to B minus A, which means for any A and B, we can always find X and Y such that A and B is the result of transformation of X and Y. And we can conclude that T is onto. There is a theorem for checking one-to-one. So if we have a linear transformation T from V to W, then T is one-to-one if and only if kernel T is only consists of the factor zero factor. Or we can say that the dimension of the basis of kernel T is equal to 0. So, for example, let's say we again have the previous transformation. We talk about when we give example for onto. To check if the transformation is one-to-one, we can check the kernel of T. If it is only consists of 0 factor, then it is one-to-one. Back to the transformation, we know that the matrix transformation is 1112 because again, recall the previous topics. Matrix transformation we got from T of a vector is a matrix transformation times the vector itself. So this is the matrix transformation. And by doing elementary basic operation, we to extend the matrix to extended matrix of this, we can obtain the result is matrix identity on the left, which means the dimension of the kernel of T is 0, or we can say that kernel of T only consists of 0 vector. So that T is 1 to 1. Another example, let's say we have a transformation from 4-dimensional space to 2-dimensional space. It is a linear transformation that is defined like this. So we have 4-dimensional space and we turn it into 2-dimensional space. And we want to check if it is onto transformation. And also if it is 1-to-1 transformation as well. So from the definition, we can first find the metric. For onto transformation, we can see here the point is for onto. Again, we have a domain. We have a codomain. Yeah. Oh no. I think no. Wait. Okay. Wait, I will stop sharing first. Are we in 1-to-1 and onto example? Oh, okay.
I can see page 1-to-1 and on to example.
Yeah, that's true. Sorry, can I, what? It's not really clear. Oh, okay, wait. Is it shown now? Okay, no worries. Okay, so back to the example we have. So for 1-to-1 and onto here, we have a transformation linear from 4-dimensional space to 2-dimensional space. And then here we want to check if it is an onto transformation and also if it is a 1-to-1 transformation. So here we can see again for onto transformation, it means when we have a domain and also codomain, then every member of the codomain must be a result of at least one transformation of one member of the domain, right? It means if we have an arbitrary vectors in the codomain, which is in this case, we are in the second two-dimensional space. So if we have a vector in two-dimensional space, let's say we have xy, it must be a result of transformation of a four-dimensional space, let's say A, B, C, D. So is arbitrary xy have an factor in R4 such that the transformation of the R4 factor is equals to the xy. And here, let us observe a factor in R4, which is xy00. And we know that by the definition of the transformation of T, A, B, C, D will be equal to AD, A plus D, and B plus D, which means if we have this as the A, B, C, D, it will always be equal to XY, which means if we have arbitrary XY, we can always get the four-dimensional space vector such that the transformation of the vector is equal to xy, which means, again, the transformation is onto. So there are various ways to show that if transformation is onto. We can give an example like this. So here we can check if the kernel of T only consists of zero vector or not. Here we can see the matrix transformation of the transformation T. Because here we have A plus D, B plus C, we can write it as a matrix times A, B, C, D. And it is equal to 1, 0, 0, 1 because we have A plus D here. And then the second one, because we have B plus C, we have 0, 1, 1, 0. So this is the matrix transformation of T. And from the matrix transformation itself, here we don't need elementary basic operation anymore because we can see that the kernel T is this. So the basis is this two. Okay, which means the dimension of the basis of kernel T is 2. It is not 0, which means the transformation is not 1-to-1. Next, we'll talk about an inverse of linear transformation. As you maybe recall, if we learn about a function in general, if a function is a one-to-one function, then we can define an inverse of the function, right? Similar to that, for linear